So in the previous class we have studied frequency response analysis using Nyquist plots. You have seen how to deduce the expression. If the number of expressions or number of poles and zeros are more, then it is very difficult to simplify. Last problem, 4s plus 1 divided by s square, that problem, 3 trigonometric function tan inverse of something something. So you got 3 tan terms there. Simplification of that consumes time. Whenever the poles and zeros are more, Nyquist plot is time consuming. Whenever the poles and zeros are more, in such cases, we will be using the Bode plot or logarithmic plot. Bode plot, it is a plot of logarithmic magnitude versus frequency and phase angle versus frequency. Here, basically there will be two plots. One is magnitude versus frequency and another one is phase angle versus frequency. And here, the magnitude and phase angle you have to write one below the other. First you have to write magnitude plot only, then below that you have to write phase angle plot. So for that we will be using semi-log sheet, that is a semi-log sheet what we have shown here. So semi-log sheet, it is a logarithmic plot. In that we will be using this. In the examination, first page there will be a graph. Behind the graph there will be a semi-log sheet. So please look the semi-log sheet and write. You cannot write this in a ordinary paper. So you have to write in a semi-log sheet only. Here in the semi-log sheet you have to accommodate both the magnitude as well as phase angle plot. When I take the stability analysis using Bode plot, I will tell you the significance of why magnitude plot and phase angle plot should be plotted one below the other. Let us see what is log of magnitude. In the previous sessions, in the Nyquist plot, directly you will be calculating the magnitude. Magnitude will be square root of real part square plus imaginary part square. So here the magnitude you will be taking in a log scale. So whenever there is a magnitude, so 20 log 10 of, what is the magnitude? Real part square plus imaginary part square. So this is the thing what will be added. 20 log 10, it is a conversion from omega in radian per second, frequency in radian per second, to frequency in decibels. We will be expressing magnitude in terms of decibel. It can be plus or minus 20. I will tell you in detail what exactly is that. But remember, 20 log 10 is the conversion from omega in radian per second to omega in decibels. Then, what are the advantages of Bode plot? Already, since it is a logarithmic plot, the log have advantage like this. Log mn. What is log m? Log m plus log n. If there is a multiplication, you can split. Then log m by n. What is log m by n? Log m minus log n. So this is the very biggest advantage in the Bode plot. Wherever there is a multiplication function, that will be converted to addition. Wherever there is a division, that will be converted to subtraction. The same thing, that is a first advantage in the log plot. And because of this flexibility, plotting the log graph is very easy. It is relatively easy. Just you have to calculate what is the magnitude in terms of decibels and what is the phase angle. Phase angle already you know how to calculate. Same thing you will be calculating in the polar plot in between values. The same expression will be there for phase angle and same thing you will be calculating for number of values. That is the advantages here. Only the change is magnitude. Here calculation of magnitude is very simplified. I will tell you when I take up the terms. It is very easy compared to Nyquist plot. This is very easy compared to Nyquist plot because of this flexibility. And in the Nyquist plot, locating n circumference about the critical point minus 1 plus j0. So that is a reference for relative stability concept. And that location of minus 1 plus j0 is somewhat hidden. Based on the Nyquist plot in g of s, h of s plane, you will be calculating whether there is any encirclement about the negative real axis or not. If there is any encirclement, then you will be locating minus 1 plus j0. Basically in the Nyquist plot, the parameters are not so visible easily. There are some hidden concepts. Based on that you will be locating, and lastly you will be writing n minus 1 plus j0 is equal to z RHS minus p RHS. Again that is also somewhat invisible. It is a hidden calculation. But Bode plot is not like that. Bode plot is not like that. All the parameters are visible. What are the parameters? In the Nyquist plot, the frequency domain specification. Have you plotted any frequency domain specification in the Nyquist plot? No. Have you shown gain margin? Have you shown phase margin? Have you shown phase crossover frequency? Have you shown gain crossover frequency? No. In the plot, we cannot show all the frequency domain specifications in the Nyquist plot. Whereas in Bode plot, you can show all the parameters and all the parameters are visible. You can show phase margin, you can show gain margin, you can show phase crossover frequency, you can show gain crossover frequency. So these things you will be calculating in the Bode plot, and based on gain margin and phase margin, you will be concluding whether the system is stable or not. Let us recall the concept. What is the condition for the stable system? The condition for the stable system is the gain margin and phase margin must be positive. What is the unstable condition? The gain margin or phase margin. If one of them is negative, the system tends to become unstable. So you will be seeing the value of gain margin, you will be seeing the value of phase margin. Also you will be seeing whether the system is stable or not. This is having a parameters visibility in detail in the plot itself. So whenever the parameters are visible, then suppose if the system is going to be unstable, then we can adjust the values so that we can bring the system into a stable condition. That means we can modify the values easily. Modification will be very easy in case of Bode plot since all the parameters are visible. When I take up the plot, you will be knowing all these things. This is very easiest calculations, not so bigger one. Just you have to understand how to locate the points, that's all. Then let us see what are the different types of terms involved in Bode plot. Again, in frequency domain analysis, the first thing what you have to consider is open loop transfer function only. Always left hand side there should be a g of s, h of s term, open loop transfer function. So look at this, g of s, h of s, open loop transfer function. This is the standard representation of Bode plot. The same concept, numerator will be telling you what are the zeros in the open loop transfer function, denominator will be telling you the number of poles, and these terms can be in numerator or in denominator. Apart from these four terms, you won't get any other things. What are these? You have a constant term. This constant can be in numerator or can be in denominator. So I will write k or 1 by k. Then poles at origin term. So that I will be writing s plus or minus n term. It can be in numerator, it can be in denominator. Then 1 plus st terms. 1 plus st, it can be in numerator or in denominator. Then s square term. So s square plus 2 zeta omega ns plus omega n square. This term plus or minus n. So there are totally 4 terms. And we need to analyze what are the characteristics of each term. Let us take first term, that is a constant term. The constant term is independent of frequency, hence the plot will be a constant. Whenever the value of k is positive, it should be above 0. Whenever the value of k is negative, it should be below 0. But remember, you have to plot the value of k in terms of log scale. So there will be a conversion 20 log 10k. 20 log 10k. More so ever, you can use 20 log 10 of 1 by k also if it is in denominator. So this is the value. If k is positive, it will be located above the 0. If k is negative, it will be located below the 0. You have to write phase angle below this, but since it is a constant term, I have written here. Here again the value will be positive, and If k is positive, the phase angle is positive. If k is negative, the phase angle is also negative. So that is the interpretation what we are drawing in constant factor. So these things you will be knowing whenever we draw a plot, whenever we solve a problem, these things will be in your fingertips. Just for the sake of explanation I will be telling. Second thing is, second term, s plus or minus n term. What is this? This represents the poles at origin or zeros at origin, this term. So what is the power of s? S can be taken 1, it can be taken 2, it can be taken 3, so it is plus or minus n. If s is positive, then it will be 20 log 10 of omega, 20 log 10 of omega. If s is negative, then again minus 20 log 10 of omega. If s is having nth power, plus n 20 log 10 of omega. If it is s is having negative, minus 20 log 10 of omega. How did you got omega here? S is equal to j omega, so 0 plus or minus j omega is the complex function. If you calculate magnitude for this, what is the magnitude? Magnitude will be square root of real part square plus imaginary part square. Real part square is 0, square root of omega is omega. This is the magnitude of in radian per second, but you have to convert that to a decibels. So this is the conversion. You will be solving magnitude of this and you will be writing here directly. Again, phase angle. How to calculate phase angle? Omega by 0, it is tan inverse infinity 90. The same thing, this is a plot here. Whenever you got s is equal to 1, then it is 20 log 10 omega. S is equal to 2, 2 into 20 log 10 omega. S is equal to 3, 3 into log 10 omega. So if it is having plus n, you will get plus n here. N will get multiplied. If you are having minus n will get multiplied. So the magnitude interpretation is, what is the power of s? If the power of s is 1, 1 into 20 log 10. If the power of s is 2, 2 into 20 log 10. If the power of s is n, n into 20 log 10. Similarly, if the power of n is negative, minus 1, if the poles at origin are in denominator, if there is a poles at origin, obviously the s term will be in denominator, because denominator represents the poles at origin. For poles at origin, you will be getting the value of n as negative. If you have one pole at origin, s is equal to minus 1 into 20 log 10, minus 2 into 20 log 10. If it is minus 3 into 20 log 10. That leads to negative slope. So this is a slope. I will tell you what exactly the meaning of decades when I take up the problem in the log sheet. So it is 20 log 10 decibels per decade. So you will get 20 decibels per decade. And here 20 decibels per decade, the slope you will get positive. So this is 0, this is 20. If you locate 20 here, this is 20 log 10 or 20 decibels per decade. So this is the positive slope. If you are having negative value, this is a negative slope. It can be 0, it can be minus 20. So minus 20 decibels per decades. So this is the interpretation of magnitude. Interpretation of phase angle is, if you get n is equal to 1, 90 degree, n is equal to minus 1, minus 90 degree. So in all the problem you will get, just you think is you have to solve for magnitude. That is the one of the important thing here. Phase angle calculation remains same. The next case is, next term, 1 plus st plus or minus n. Here there is no real part. There is only imaginary part, that is j omega, but here there is a real part as well as imaginary part. Will it make difference? Yes, absolutely it will make difference, but the magnitude calculation remains same. Whenever you want to solve for magnitude, first you find out what is the power of s. What is the power of s here? S is having a linear power. S is equal to 1. If the value of s power is 1, then it will be 20 log 10 of magnitude. 20 log 10 of magnitude. Suppose 1 plus st whole square, what is the power of s? 2. 2 into 20 log 10. So first we will be locating the power of s here, it will be 1, so 20 log 10 omega, then we will be multiplying what is the index plus or minus n. So the same thing, if you have s power 1, 20 log 10 of magnitude, if you have s power 2, 2 into 20 log 10, s power 3, 3 into log 10, if s is minus 1, minus 1 into 20 log 10, if s is minus 2, minus 2 into 20 log 10. This calculation is almost same, only thing is indexed. But what is the change here? Here there is a change of magnitude. What is the magnitude of 1 plus st? So 1 plus j omega term, 1 plus j omega, magnitude will be square root of real part square, 1 square plus imaginary part square, omega square. But here you have to simplify the expression in terms of 1 plus st term. Then it will be very easy. What is that? St. So what is the value of t here? So t will be calculating using omega c. Omega c is nothing but it is a corner frequency or break frequency. It will take break. How long I need to extend this line? Up to infinity? Don't know. Up to some value, that some value itself is the corner frequency. That means where this value meets omega t greater than or 1, omega t less than 1. That means where I need to extend this line, how long I need to extend this line. So I need to extend the line up to what? Some corner frequency. Then again the magnitude changes. Up to some corner frequency. Again up to some corner frequency. That is the interpretation for this term. So that's why it will be omega square plus t square with a root, and this is the magnitude of this complex function. Then 20 log 10, the conversion of omega in radian per second to omega in decibels, magnitude in decibels. Then this value is having a constant magnitude, but this value is having magnitude in decibels. That is very important thing. Then the same interpretation for phase angle. Here also you will get plus 20 minus 20. The same slope is being determined here. Next term is s square term. S square term is always challenging in calculating the phase angle, not for magnitude. What is the magnitude for this? Before that, what is the power of s? The power of s is 2. Since the power of s is 2, magnitude will be 40 log 10. This is what we have written, 40 log 10. But here there can be any number of n, s square plus 1 whole square, that can be there. What is the magnitude calculation? Again, index you multiply plus or minus n. S square, if power of n is 2, 2 into 40. S square, power of s is 3, 3 into 40. Since it is a s square, it is 40 log 10. But how to calculate this part? This part is very important. There will be one root here. I will tell you how to solve that. First I will consider s square plus 2 zeta omega n s plus omega n square. This you have to remember, very important. Already you have solved some of the problems in time response analysis, because here what is the corner frequency? The corner frequency is omega n only. You have to compare the given equation in the standard form. This is a equation in standard form. Here omega n will be equal to omega c. Corner frequency is nothing but natural frequency of the system, and you have to calculate what is the value of zeta also. How will you calculate? By comparing the expression. Let us see how to do this. I will consider this as a z, s square plus 2 zeta omega ns plus omega n square. Replace s is equal to j omega, then j omega whole square plus 2 zeta omega n into j omega plus omega n square. So what I will do is I will divide this with omega n square, then j square omega square divided by omega n square plus 2 zeta omega n into j omega divided by omega n square plus omega n square by omega n square is 1. So this term will get cancelled. What I will get is, I will be segregating real parts on one side, imaginary part on other side. What is j square? J square is minus 1. So it will be omega square by omega n square plus 2 zeta omega by omega n into j plus 1. So what is the real part? Real part is 1 minus omega by omega n whole square, and imaginary part is 2 zeta omega by omega n into j. So this is a real part and this is an imaginary part. What is the magnitude? Magnitude will be equal to square root of real part square 1 minus omega by omega n whole square plus imaginary part 2 zeta omega by omega n whole square. This is the magnitude of the plot. What is the phase angle? Phase angle will be tan inverse of imaginary part. What is the imaginary part? 2 zeta omega by omega n divided by real part. What is the real part? 1 minus omega by omega n whole square. And these are the expressions in vibrations which is located at denominator. You will be having the same function in vibrations. So this is how you got this value. But here you have to take precautions while solving this in calculator. Whenever you give omega is equal to omega n value, the denominator becomes infinity. What is tan inverse of infinity? 90 degree. So 1 minus 1, it will be 0. Anything by 0 is infinity. What about that after values? If omega n is equal to 6 radian per second, omega is equal to 7 radian per second, then this value tends to become 180. That means the value is being shifted. So you have to multiply with minus 180 there. I will tell you what exactly is that whenever take up the problem. So this denominator you have to take precaution. When omega is equal to omega n, it will not shown in calculator. That is the thing you have to remember here. Rest of the calculation remains same. So this is about 4 terms. Simply what we can see is how to write magnitude plot. Whenever the power of s is 1, plus 20 decibels per decade. Whenever the power of s is minus 1, minus 20 decibels per decade. Similarly, for 1 plus st term, 20 log 10 of magnitude. If it is negative power, minus 20 log 10 of magnitude. S square, 40 log 10 of magnitude. These are all log 10. While solving this in calculator, you have to use log 10, or just you can use log. Don't use ln. Don't use ln. This is very important here while solving in that calculator. So this is about the terms in Bode plot. The next topic is stability analysis using Bode plot. Some of the terms you have seen: k terms, s terms, 1 plus st terms and s square term. So those things cumulatively we will got the magnitude as well as the phase angle plot. First let us see how to analyze the stability. Before analyzing the stability, first you have to draw a Bode plot. How to draw a Bode plot? Bode plot is a plot of logarithmic magnitude versus frequency and phase angle versus frequency. Here phase angle is not in decibels, only the magnitude will be in decibels. So I will write this is a magnitude versus omega. Magnitude versus omega. Similarly, another plot, this is in log magnitude, that is in decibels, and this is phase angle and omega. What is omega? Omega is the frequency. Frequency will be in radian per second. Radian per second. Usually in the magnitude there will be a reference line what we will take for analysis. This is a reference which is called as 0 decibel line. Reference is 0 decibel line. Similarly for the phase angle plot, the reference will be taken, that reference will be minus 180 degree line. This is a reference line. What is the reference here? Minus 180 degree line. So if I plot the magnitude, the plot might be like this. So it will be something like this. So before that I will mark this is 0 decibel, this is 20, this is 40. As such, the plot might be like this. It will go like this, and phase angle will be like this. So these are the two plots, magnitude plot. This is a magnitude plot, and this is the phase angle plot. After simplifying the terms, we will be getting this. Usually magnitude plot will not be a smooth curve. Generally it will be a straight lines. Just here, for just simple analysis, I have written like this. And this is phase angle in degrees. After this, what I have to do? First, we draw magnitude plot, then phase angle plot. We have marked the references. The reference for magnitude plot is 0 decibel line. The reference for phase angle plot is minus 180 degree line. It is just to obtain phase crossover frequency and gain crossover frequency. So this is minus 180 degree. So let us identify the magnitude plot crosses 0 decibel line. So this point, the intersection of magnitude plot at 0 decibel line, project this to a phase angle plot. So the point at which the magnitude plot touches 0 decibel line, that is called as magnitude plot corresponding to gain, and this is also corresponding to gain. So this is called as gain crossover point. After that, you project gain crossover point to phase angle plot, where the phase angle plot touches this projection line. The distance from that point to minus 180 degree line is nothing but it is phase margin. And you still project the line and you will get, that is gain crossover frequency. This is how to get phase margin. First we draw magnitude plot, then phase angle plot, then we located gain crossover point. Gain crossover point is the point where the magnitude plot touches 0 decibel line. Similarly, after that what we have done, we have projected the gain crossover point to phase angle plot, and the distance where the magnitude plot projects to the phase angle plot to minus 180 degree line, that is nothing but it is the phase margin. Then similarly, I will locate the same thing for phase angle plot. The phase angle plot, what is the reference here? It is minus 180 degree line. So phase angle plot touches minus 180 degree line. That point is called as phase crossover point, and the frequency corresponding to that is called omega p or PCF, phase crossover frequency. Then after that, again I will project the phase crossover point to the magnitude plot. See the directions here. I have written the directions. First I need to project gain crossover point to phase angle plot, then phase crossover point to magnitude plot. So the distance where the projection point of phase crossover point touches phase angle plot to 0 decibel line, this distance is gain margin. For the stable system, the gain margin and phase margin must be positive. In the previous sessions, we analyzed how to get positive gain margin and negative gain margin for the Nyquist plot, but here how to get positive gain margin and negative phase margin here. What is gain margin? Gain margin is 1 divided by magnitude of G of S H of S, 1 by magnitude of open loop transfer function. So 1 by A, it is additional gain required to make the system just unstable. So you calculate what is the magnitude for this. Magnitude is 1 by A. So if I want to convert that to a log scale, 20 log 10 1 by A. In other words, minus 20 log 10 A. Whenever I want to give the value of gain margin to a positive, if I want to make the value of gain margin to be a positive, this term should be positive. How to make positive? Already there is a minus. So log of minus will make this term as a positive. So here A should be a compulsory negative. So A negative means it should be below 0 decibel line. So here, since gain margin is below 0 decibel line, you will get it is positive. Then let us analyze phase margin. What is phase margin? Phase margin will be equal to 180 degree plus phase angle of open loop transfer function. If you want phase margin to a positive, it should be above minus 180 degree line. It should be above minus 180 degree line. So this is minus 180 degree line. It should be above minus 180 degree line. That means here it will be minus 90, minus 45 as such. But below this it will be minus 225, etc. So if the value crosses beyond 180, so 180 minus 190, it will be minus. So hence this term should be above minus 180 degree. In order to make phase margin as positive, here also phase margin is above minus 180 degree line, hence it is positive. If gain margin and phase margin are positive, that means gain margin is above 0 decibel line and phase margin is, gain margin is below 0 decibel line and phase margin is above minus 180 degree line. When you get gain margin and phase margin are positive, when gain margin is below 0 decibel line and phase margin is above minus 180 degree line, at this condition you will get gain margin and phase margin are positive. Since the gain margin and phase margin are positive, this is the condition for stable system. If the graph looks like this, it is a stable system. What about for unstable system? Gain margin and phase margin will be negative. It is another plot. That means you will get GCP after PCP. So look at the graph. Look at the graph. You will be seeing what is the gain margin, what is the phase margin, what is gain crossover frequency and what is phase crossover frequency. Also clearly you are seeing whether the system is stable or not. That means the performance parameters of frequency domain specifications is clearly visible in case of Bode plots. By seeing this, if the value of gain margin, suppose if it is a negative and phase margin is a positive, by looking into that we can say the system is stable. Suppose if one of them is negative, gain margin is negative, then we can adjust how much value is to be adjusted. That also you can see here. By seeing into this, you can adjust that value. That means modifications of the system will be easily done. So basically what we have done here, first we have drawn magnitude plot, then phase angle plot, then identify the magnitude plot crossing 0 decibel line. That means you have to identify the intersection of magnitude plot and 0 decibel line intersection point, that is phase crossover point and gain crossover point. And by projecting the gain crossover point to the phase angle plot, you will get phase margin. By projecting phase crossover point to the magnitude plot, you will be getting gain margin. After that, find omega g and omega p, gain crossover frequency and phase crossover frequency, and comments on stability. This is how we will be analyzing the stability using Bode plot. Let us solve some of the problem. In the problem, these things are common. Let us see how to solve a problem. So it is a basic procedure to construct a Bode plot. The first thing is you need to have a semi-log sheet. It is not possible to draw in a graph sheet. You have to use semi-log sheet only. The first step is rewrite sinusoidal transfer function in a standard form considering open loop transfer function. As already I said, in frequency domain analysis, always we will consider open loop transfer function for the analysis. What is the standard form? This is the standard form, k into 1 plus st1, 1 plus st2, etc. There might be a square term in the numerator also, divided by s to the power of 1, 1 plus st, 1 plus st, etc. Suppose s plus 1 is given, convert that to 1 plus st form, 1 plus s. S plus 2, take 2 common. This is something like this. If s plus 1 is given, make that 1 plus s. If s plus 2 is given, take 2 common. So it is 1 plus s by 2. So you have to take the expression in terms of 1 plus st form. What is the value of t here? 2. 1 by 2, t is 1 by 2, omega c is 2. In order to calculate the frequencies, corner frequencies, we are modifying in 1 plus st method. Then after that, identify the corner frequencies. For 1 plus st term, corner frequency is 1 by t. For second degree term, s square term, the corner frequency is omega n. Very important thing. Whenever you got s square term here, you have to compare s square with standard form. Then you have to get what is zeta and omega. Suppose s square plus 2s plus 4. This is a term we got. Compare this with standard form. S square plus 2 zeta omega ns plus omega n square. What is 2 zeta omega n? 2. What is omega n square? 4. Omega n is equal to 2. So this omega n is equal to 2. It is just an example. This itself is omega c here. And what is the value of zeta? Why we want zeta there? In phase angle we need zeta. 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. So zeta omega n is equal to 1. So zeta is equal to 1 by 2. So this is how you need to calculate the zeta and omega n for second order system, s square terms. So this is common in all the problems when you got s square terms. This is very important. You have to compare with standard expressions. After that, by knowing the corner frequencies, you have to arrange corner frequencies in ascending order. Another important step. After arranging the corner frequencies in ascending order, you have to draw a magnitude plot. How to draw a magnitude plot? Again, power of s is determined. If s power is 1, it is 20 log 10. S power is 2, 2 into 20 log 10. Like that it will go. Again, here, whenever there is a s term involved in the function, then it consists of a straight line segments with the line of slope. Here, whenever there is a term of s, we will take a slope. It will be an inclined line. So 0 to 20 we will join, and that will be a slope. Here, a line of slope at each corner frequencies will be determined, and cumulatively we will add, we will get magnitude plot here. Whenever you have only zeros and poles at origin, then this is plus 20 minus 20. Second case, whenever you have a poles and zeros with multiplicity n, that is 1 plus st plus or minus n. Whenever there are zeros means the s terms will be in numerator, you will get n as a positive. Whenever there is a s terms are in denominator, those are referred to as poles. Denominator terms are poles. It's the same thing. So if this is in denominator, minus n. The index what you have to take. By seeing into the index, you have to able to locate whether it is a pole or zero. If it is plus n, it is a 0. If it is minus n, it is a pole. Because the s terms will be in denominator, denominators will represent the poles. Then, for complex zeros and complex poles, in other words, it is for s square terms. Whenever there is a s square terms in the problem, that refers to a complex zeros or poles. So if there is a complex zero, that means s square term will be in numerator, the power of index will be n is equal to 1. Since s square is already there, the slope for s square term is 40 decibels per decade. Then, if there is a complex poles, s square terms will be there in denominator. Since s square terms are there in denominator, the multiplicity will be minus n. So, by looking into this, you have to locate whether it is having s square term or not. This concept is very important here. Magnitude only 3 cases. One is plus 20, another one is n into 20, another one is n into 40, plus or minus n. So that's all the cases. Whenever we take up the magnitude plot, this will be easy for you. This is all corresponding to magnitude plot. You have to consider cumulative slope in magnitude plot. After that, draw a phase angle curve for each factor and add them algebraically to get phase angle plot. Again, what is the calculation of phase angle that you know? Phi is equal to tan inverse of something, something, something. The procedure what you have solved in the Nyquist plot is same. Directly writing the equation for a phase angle and solve that using in your calculator. There is an option called as solve. By giving the values, you can get what is a phase angle for different values of frequencies. Then finally, after drawing phase angle plot and magnitude plot, in the log sheet, determine phase crossover point. Phase crossover point is the intersection of magnitude plot in 0 decibel line. Similarly, project phase crossover point to the magnitude plot, phase angle plot. After locating phase crossover point and gain crossover point, next step is stability. Stability is just first you have to draw phase angle plot, then magnitude plot. After the fourth step, then you have to draw magnitude plot as well as phase angle plot in the log sheet. After drawing magnitude plot, after drawing phase angle plot, locate the reference for magnitude plot and locate the reference for phase angle plot. The reference for magnitude plot is 0 decibel line. The reference for phase angle plot is minus 180 degree line. Otherwise, before taking the scale itself, you can make 0 decibel line as a darker line and minus 180 degree line as a darker line. So those two are the reference for magnitude as well as phase angle plots. After this, draw the magnitude plot and draw the phase angle plot. After drawing magnitude and phase angle plot, identify whether the magnitude plot is crossing 0 decibel line or not. If it is crossing, then identify the intersection point where the magnitude plot crossing 0 decibel line and name that point as gain crossover point. After naming gain crossover point, project gain crossover point to the phase angle plot. And the gain crossover point projection is touching on phase angle plot and locate the distance. So the distance from intersection of projection point on gain crossover point to minus 180 degree line, that is called as phase margin. So first part is over. You have calculated phase margin using gain crossover point. Similarly, identify phase angle plot is crossing minus 180 degree line. The point at which phase angle plot touches minus 180 degree line, that is called as phase crossover point. Locate that. Project the phase crossover point to the magnitude plot and identify the projection of phase crossover point touches the phase angle plot. And the distance between the projection point on phase crossover point to 0 decibel line is called as gain margin. Locate the gain margin and count how many divisions, multiply by scale, you will get the gain margin. Phase margin, gain margin, got it. And gain crossover frequency, gain crossover point, locate to the frequency plot, frequency line, you will get gain crossover frequency. Similarly, phase crossover point, project it on frequency line to get phase crossover frequency. So gain margin you got, phase margin you got, and phase crossover frequency you got, gain crossover frequency you got. After seeing the values, identify whether the system is stable or not. For the stable system, gain margin and phase margin must be positive. If gain margin is positive, that means it should be below 0 decibel line, and phase margin to be positive, it should be above minus 180 degree line. If these conditions are there, if the gain margin is below 0 decibel line and phase margin is above minus 180 degree line, the system is stable. That means for the stable system, the gain margin and phase margin must be strictly positive. If one of them is negative, the system is unstable. That is all the comments you have to write. So this is how to analyze problem. First, open loop transfer function. Here, extra thing is you have to write the open loop transfer function in a standard form, then magnitude plot, slopes, then phase angle plot, direct equations and solving in calculator, then draw the phase angle and magnitude plot. Why in the first session I told you have to draw magnitude plot and phase angle plot one below to other. Why means those two are interdependent. You have to adjust the scale in such a way that. Then after that, after plotting, analyze the stability. This is all the procedure in the problem. Let us solve one problem to understand the procedure. We'll be solving around 4 to 5 problems so that it will be easy for you. In the examination, one problem will be there for 20 marks. Just they will give open loop transfer function and you have to solve using this. And in the question itself, they will mention solve using Bode plot, solve using Nyquist plot, like that it will mention. You will get 2 questions. Very good chances is 20 marks from Nyquist plot, 20 marks from Bode plot, that is one possible. 8 marks in polar plot, 12 marks in Nyquist plot, one question, one Bode plot question, it is also possible. I don't think that 10 marks in Nyquist plot and 10 marks in Bode plot question to be asked here, because all the problems are somewhat lengthy. That should be having weightage for 20 marks. Let us solve the problem.